An aurora, sometimes referred to as a polar light, is a natural light display in the sky, predominantly seen in the high-latitude regions. Auroras are produced when the magnetosphere is sufficiently disturbed by the solar wind that the trajectories of charged particles in both solar wind and magnetospheric plasma, mainly in the form of electrons and protons, precipitate them into the upper atmosphere, where their energy is lost. The resulting ionization and excitation of atmospheric constituents emits light of varying color and complexity. The form of the aurora, occurring within bands around both polar regions, is also dependent on the amount of acceleration imparted to the precipitating particles. Precipitating protons generally produce optical emissions as incident hydrogen atoms after gaining electrons from the atmosphere. Proton auroras are usually observed at lower latitudes. Different aspects of an aurora are elaborated in various sections below. Occurrence of terrestrial auroras. Most auroras occur in a band known as the auroral zone, which is typically 3 degrees to 6 degrees wide in latitude and between 10 degrees and 20 degrees from the geomagnetic poles at all local times. Most clearly seen at night against a dark sky. A region that currently displays an aurora is called the Auroral Oval, a band displaced towards the night side of the Earth. Day-to-day positions of the auroral ovals are posted on the Internet. A geomagnetic storm causes the auroral ovals to expand, and bring the aurora to lower latitudes. Early evidence for a geomagnetic connection comes from the statistics of auroral observations. Elias Loomis, and later Hermann Fritz and S. Tromholt in more detail, established that the aurora appeared mainly in the auroral zone, a ring-shaped region with a radius of approximately 2,500 kilometers around the Earth's magnetic pole. It was hardly ever seen near the geographic pole, which is about 2,000 kilometers away from the magnetic pole. The instantaneous distribution of auroras is slightly different, being centered about 3 to 5 degrees nightward of the magnetic pole, so that auroral arcs reach furthest toward the equator when the magnetic pole in question is in between the observer and the sun. The aurora can be seen best at this time, which is called magnetic midnight. In northern latitudes, the effect is known as the Aurora Borealis, named after the Roman goddess of dawn, Aurora, and the Greek name for the north wind, Boreas, by Galileo in 1619. Auroras seen within the auroral oval may be directly overhead, but from farther away they illuminate the poleward horizon as a greenish glow, or sometimes a faint red, as if the sun were rising from an unusual direction. Its southern counterpart, the Aurora Australis, has features that are almost identical to the Aurora Borealis and changes simultaneously with changes in the northern auroral zone. It is visible from high southern latitudes in Antarctica, South America, New Zealand, and Australia. Auroras also occur on other planets. Similar to the Earth's aurora, they are also visible close to the planet's magnetic poles. Auroras also occur poleward of the auroral zone as either diffuse patches or arcs, which can be subvisual. Auroras are occasionally seen in latitudes below the auroral zone, when a geomagnetic storm temporarily enlarges the auroral oval. Large geomagnetic storms are most common during the peak of the 11-year sunspot cycle or during the 3 years after the peak. An aurora may appear overhead as a corona of rays, radiating from a distant and apparent central location, which results from perspective. An electron spirals about a field line at an angle that is determined by its velocity vectors, parallel and perpendicular, respectively, to the local geomagnetic field vector B. This angle is known as the pitch angle of the particle. The distance, or radius, of the electron from the field line at any time is known as its Lambda radius. The pitch angle increases as the electron travels to a region of greater field strength nearer to the atmosphere. Thus, it is possible for some particles to return, or mirror, if the angle becomes 90 degrees before entering the atmosphere to collide with the denser molecules there. Other particles that do not mirror enter the atmosphere and contribute to the auroral display over a range of altitudes. Other types of auroras have been observed from space, e.g., poleward arcs, stretching sunward across the polar cap, the related theta aurora, and dayside arcs, near noon. These are relatively infrequent and poorly understood. There are other interesting effects such as flickering aurora, black aurora, and subvisual red arcs. In addition to all these, a weak glow observed around the two polar cusps. The field lines separating the ones that close through the Earth from those that are swept into the tail and close remotely. Images. The altitudes where auroral emissions occur were revealed by Carl Stormer and his colleagues, who used cameras to triangulate more than 12,000 auroras. They discovered that most of the light is produced between 90 and 150 kilometers above the ground, while extending at times to more than 1,000 kilometers. Images of auroras are significantly more common today than in the past due to the increase in use of digital cameras that have high enough sensitivities. Film and digital exposure to auroral displays is fraught with difficulties. Due to the different color spectrum present, and the temporal changes occurring during the exposure, the results are somewhat unpredictable. Different layers of the film emulsion respond differently to lower light levels, and choice of film can be very important. Longer exposures superimpose rapidly changing features, and often blanket the dynamic attribute of a display. Higher sensitivity creates issues with graininess. David Malin pioneered multiple exposure using multiple filters for astronomical photography, recombining the images in the laboratory to recreate the visual display more accurately. For scientific research, proxies are often used, such as ultraviolet and color correction, to simulate the appearance to humans. Predictive techniques are also used to indicate the extent of the display, a highly useful tool for aurora hunters. Terrestrial features often find their way into aurora images, making them more accessible and more likely to be published by major websites. It is possible to take excellent images with standard film and a single-lens reflex camera with full aperture, a fast lens, and exposures between 10 and 30 seconds, depending on the aurora's brightness. Early work on the imaging of the auroras was done in 1949 by the University of Saskatchewan using the -270 Seychelles rupees radar. Play media Aurora Borealis from the International Space Station. Aurora during a geomagnetic storm that was most likely caused by a coronal mass ejection from the Sun on 24 May 2010. Taken from the ISS. Diffuse aurora observed by the DA-1 satellite from high Earth orbit. At some times, they form quiet arcs. At others, they evolve and change constantly. The most distinctive and brightest are the curtain-like auroral arcs. Each curtain consists of many parallel rays, each lined up with the local direction of the magnetic field, consistent with auroras being shaped by Earth's magnetic field. In situ particle measurements confirm that auroral electrons are guided by the geomagnetic field, and spiral around them while moving toward Earth. The similarity of an auroral display to curtains is often enhanced by folds within the arcs. Arcs can fragment or break up into separate, at times rapidly changing, often rayed features that may fill the whole sky. Occasionally arcs display fast sub-second flickering intensity variations. These are the discrete auroras, which are at times bright enough to read a newspaper by at night. The diffuse aurora, on the other hand, is a relatively featureless glow, sometimes close to the limit of visibility. It can be distinguished from moonlit clouds by the fact that stars can be seen undiminished through the glow. Diffuse auroras are often composed of patches whose brightness exhibits regular or near-regular pulsations. The pulsation period can be typically many seconds, so is not always obvious. Often they're black aurora, i.e., narrow regions in diffuse aurora with reduced luminosity. A typical auroral display consists of these forms appearing in the above order throughout the night. In contrast to the predominantly continuous black body radiation of the Sun and other stars, the aurora is composed by light emitted at discrete emission lines of the atoms, molecules and ions of the upper atmosphere. This impacts both human color perception and photography of aurora. Red. At the highest altitudes, excited atomic oxygen emits at 630.0 nanometers. Low concentration of atoms and lower sensitivity of eyes at this wavelength make this color visible only under more intense solar activity. The low amount of oxygen atoms and their gradually diminishing concentration is responsible for the faint appearance of the top parts of the curtains. Scarlet, crimson, and carmine are the most often seen hues of red for the auroras. Green. At lower altitudes, the more frequent collisions suppress the 630.0 nanometers mode. Rather, the 557.7 nanometers emission dominates. Fairly high concentration of atomic oxygen and higher eye sensitivity in green make green auroras the most common. The excited molecular nitrogen plays a role here, as it can transfer energy by collision to an oxygen atom, which then radiates it away at the green wavelength. Both the 557.7 and 630.0 nanometers wavelengths correspond to forbidden transitions of atomic oxygen, slow mechanism that is responsible for the graduality of flaring and fading. Blue. At yet lower altitudes, atomic oxygen is uncommon, and molecular nitrogen and ionized molecular nitrogen takes over in producing visible light emission, radiating at a large number of wavelengths in both red and blue parts of the spectrum, with 428 nanometers being dominant. Blue and purple emissions, typically at the lower edges of the curtains, show up at the highest levels of solar activity. The molecular nitrogen transitions are much faster than the atomic oxygen ones. Ultraviolet. Ultraviolet light from auroras has been observed with the requisite equipment. Ultraviolet auroras have also been seen on Mars, Jupiter, and Saturn. Infrared. Infrared light, in wavelengths that are within the optical window, is also part of many auroras. Yellow and pink are a mix of red and green or blue. Other shades of red as well as orange may be seen on rare occasions. Yellow-green is moderately common, as red, green, and blue are the primary colors of additive synthesis of colors. In theory, practically any color might be possible, but the ones mentioned in this article comprise a virtually exhaustive list. Other auroral radiation. In addition, the aurora and associated currents produce a strong radio emission around 150 kHz known as auroral kilometric radiation (AKR), discovered in 1972. Ionospheric absorption makes AKR only observable from space. X-ray emissions, originating from the particles associated with auroras, have also been detected.